Codebase is a term that we've borrowed from the software world. So you may have heard people talking about what we do at Ginkgo as programming DNA. So we have DNA sequencing, which is the ability to read DNA, DNA synthesis, which is the ability to write DNA. Put those two things together, and effectively you're writing code. Codebase in the software world is really a way of thinking about what are the things that we've learned over the course of writing software programs that can be repurposed and reused for writing new programs. So a programmer today working on a new application would say, let me check out a library or a module from this code base to build a new application. They're not writing every new application from scratch. There are lots of tools available to make that easier. What we're trying to do at Ginkgo is basically build up all that experience that all the experience that we have from doing all these programs, is saying what are the biological programs from previous work that we've done and make them available to our programmers to use in subsequent projects, so that we're not starting each new project from square one, but can start on the basis of reusable biological assets or code base that we can put into new programs. The really cool thing about biological code base is that it starts with nature. So unlike every other engineering or programming discipline, biology has actually been designing new things for 4+ billion years, right? So the idea is we can actually start by looking into nature to look at genetic programs that have been produced via evolution as our starting point. But one of the interesting things about biology is that there is a lot of digital information stored all around us. There's much more biological information out there than you may be aware of. So, for example, you may know that you have 1 trillion cells in your body. On top of those trillion cells, you also have 1 trillion bacteria living in your body. So think about just the density of information that's encoded in all of those organisms. Another example for this is soil. You may think of soil as just dirt. Soil to us is an interesting place to look for new genetic programs. So to give you an example, we had a project that involved chemistry in the soil where we decided to sequence some soil to find new genetic activities. Take 50 milliliters, so that's about a shot glass worth of soil, run that through a sequencer, and what you find, and what we found, is you identify 30 gigabases of new DNA information. So, a base pair is about a bit. That's 30 billion bits of new information. All those bits represent potential new genetic programs that we can use in different contexts, right? Multiply that times the rest of the world, and you can understand that 4 billion years of evolution has created a lot of biological diversity, and therefore genetic programs that have been invented by biology that can then be identified and developed here at Ginkgo to build the next genetic program. Every time we do some sequencing like that, we're looking for new genetic functions. We test those in our foundry, and as we characterize those functions in the foundry, we record that digitally so that we can go back and reuse those genetic parts later. Codebase at Ginkgo really benefits from and exists because of the foundry. Effectively, you can think of the foundry as a way to do scalable experiments. So, really the scale that we have in the foundry allows us to collect so much information. It wouldn't have made sense to try to record information in this way until we had this method using the foundry to systematically create thousands of data points for every project. Today, we've done more than 10 million strain tests, so that information can be used to make sure that we're progressively making better decisions when we're designing new projects. Today at Ginkgo, we have certain programs that have looked at 30 to 40,000 genes. We're taking more shots on goal, iterating through more designs so that we can more rapidly engineer a working and functional organism for that customer. So that's what the foundry can do. Codebase is important because we want to take all that information that we're learning from that one project and apply it to the next one, right? So you can think about as we grow foundry capacity year over year, I want more and more of that capacity to be pointed at brand new things, right? Like doing projects that we've never done before, working in enzymatic pathways that we've never worked in before, because the code base knowledge that we're building up means that we don't have to repeat some of those same experiments that we've done previously. The kind of cool thing about biology is that given that biology all evolved from a common ancestor, a lot of biochemistry is shared across a huge diversity of products that are made by nature. So that means we're progressively learning more and more about what nature can do. So each new project will borrow more from our pre-existing code base that's like characterized genetic parts and programs that we've done before, which frees up even more foundry capacity for all the new stuff we're doing, right? So it's a virtuous cycle where we grow foundry scale, collect more data, and can make better use of that foundry scale on the basis of the data that we've already collected in our code base. Another way to think about Codebase is how many different sequences do we sift through when we're looking for a new genetic function. Today, we have a database that includes about 3.4 billion sequences collected from the broader world. These are sequences that have been collected by, all of the biological community and provided on public databases. And then we have another 400 million sequences that we've collected over the years that are proprietary to Ginkgo. And that gives you like almost 4 billion sequences to play with. But again, what I find exciting about that is sequencing, as you may know, is getting cheaper and cheaper and more scalable each year. So the cost of sequencing has fallen a millionfold over the last 20 years. So ultimately what that means is in terms of looking for new genetic sequences and new genetic code, we're really just getting started. And those hundreds of millions of sequences that we have today represent a small sliver of the sequences that we'll be using a few years from now to identify new gene functions. In many ways, Codebase is a literal parts library. Right? We have genetic sequences that we have in our databases that correspond to actual DNA sitting in a freezer that an engineer can put to use in a new project. The data about those parts, the performance data, is what helps us make good decisions there. But ultimately, what's cool about Codebase is that it is physical. It is genetic sequences that can be repurposed. It is organisms that we've used across a large number of programs, and that ability to identify new genetic parts out in nature and then put them to work in our foundries is one of the things that I'm really excited about, because as our foundries grow, so does our ability to identify new genetic functions and learn from nature. And ultimately, what we're trying to do as engineers is making sure that we're learning from the 4 billion years of genetic experimentation that have already happened ahead of us. That's a tremendous resource that you just don't have in other engineering disciplines. We actually can learn so much from what nature has already done for us, and we finally have the tools to do that. How does Codebase benefit our customers, right? So we have two different types of customers. Many of them actually are cell programmers in their own right? So they've been engineering biology for many years. They have deep expertise in their organisms and their programs. But again, they've been very focused on a certain set of products, right? So what Codebase offers is saying, here are all the genetic parts that we've looked at over the course of doing dozens of different programs, probably working on organisms and market verticals and applications that have nothing to do with what this customer is working on. And yet, because biology is really cool, we often find functions that can be repurposed for those customers, right? So they're automatically benefiting from the dozens of programs that we've performed on day one. The other type of customer that we work with, these are product companies. They're really focused on developing compelling new products with biology, right? So they're interested in formulation, generating new materials, basically trying to get products to consumers, right? What Codebase offers them is they don't need to build out deep expertise in terms of what genetic design to use when trying to overexpress a new gene in a new system. They can work with us, and we can say, your product resembles another project that we've done before. Therefore, we can start with this host organism that produces precursors for your project, or we can start with this host organism that's very talented at producing protein. Here are genetic approaches that have worked before. We can apply that to your particular program. And ultimately, for those customers, it means they spend much more of their time thinking about how to make their products rather than trying to think about the organism that makes their products, which is really our job. How does Ginkgo as a horizontal platform differ from kind of the traditional way of engineering organisms? Many of our predecessors in this space would have focused on a very narrow set of products to produce. So imagine that you're starting a new biological product company today. If you didn't know that Ginkgo existed, what you would probably do is you'd go out and you'd hire 20 PhDs, right? They'd all work at the bench. They'd be very smart, come up with good ideas. A lot of person hours of work would go into engineering a small number of engineered organisms. If you're lucky, you'll end up with a product at the end of that. At Ginkgo, what we're doing is instead you have a 5-person team because they're making use of the foundry to do most of their work. They're starting from a point where they can say, start with a existing protein expression strain that we've already developed. So a lot of the initial work you would do just to get started has already been done. And then the know-how and approaches you'd use to leverage the foundry to look at thousands of new prototypes to rapidly optimize your strain, those are lessons learned that we've incorporated across dozens of projects. So ultimately, what we offer to customers who are trying to start new programs, create new biological products, is that they don't have to assemble those 20 PhDs. They don't have to build all of that institutional knowledge that will only live on in a single product. They can benefit from the institutional knowledge that we've collected across dozens of programs. So one way that we're thinking about Codebase is how do we actually package Codebase as more understandable, both for our cell programmers, but also for our customers. One organizing principle that's been really useful in software are what are called SDKs. That stands for Software Development Kits. An SDK will give you the tools to program in that language. It'll give you some example libraries, some code base that you can use to build higher order programs. And it'll also give you documentation, right? So you put those things together, and a new programmer can get up to work quickly working in a new programming language. So we're trying this out at Ginkgo, calling them CDKs or cell development kits. But effectively what a CDK is for Ginkgo is taking an experienced organism that we've used across a number of different programs. So we know that it has robust performance. We know it grows well in a fermenter, works well in our automation and our foundry, so the robots can work with it. And importantly, we also have tools, so our foundry tools can be applied to that organism. Combine that with documentation, you basically have a platform that enables us to help our cell programmers get up and running quickly with a new program. So, for example, with the Dushinei organisms that we're bringing over, these are filamentous fungi. What we're doing is we're building a fungal CDK, which will basically take those organisms, make sure that we have foundry tools to do all the things that we can do in the foundry with these organisms, and use that to build out a number of different programs focusing on protein expression and enzyme expression. And ultimately what that does is it creates not only the playbook for executing these types of programs, but it also builds out the tools and documentation. So again, leveraging hard-won lessons from software to say, let's make sure that these projects are repeatable and that we never make the same mistake twice on a program. And CDKs are just one organizing principle for that. What's exciting about Codebase is that we're just getting started. We've accumulated more than 10 million strain tests since we've opened our foundries, and each of those strain tests generates data that helps us inform how we should use our foundries better, right? But ultimately, you've probably heard of Knight's Law. That means that year over year, our ability to generate data continues to grow, right? So really, we're just learning how to collect and catalog that data in better and better ways. That's really where we start to see the benefits of these dramatically falling cost curves in DNA sequencing and synthesis. It's not just about reading and writing code, but learning from that code. And if we're able to learn at the same rates that we've been able to improve the underlying technology, biology is going to get a lot more easy to engineer over the next few years.
My name's Claire Laporte, and you've just heard about Foundry and Codebase from some of the other folks here. And I'm here to tell you about what that means from an intellectual property standpoint, how we protect it, and what it means for our customers. Well, I came to Ginkgo in 2018 after 28 years at a law firm. I was doing patent trial work, and I also advised little companies that were getting ready to go public or get acquired, deal with their intellectual property problems. So I came to Ginkgo to develop a strategy for the IP of this rapidly growing company and to figure out how to fit IP into the unique situation of Ginkgo. Ginkgo is like a giant invention factory where literally hundreds of brilliant ideas are made every single day. And so the question is, what do you do to protect all of that? You can't patent hundreds of new things a day. That would take an administrative empire, which is certainly not an efficient way to run a company. And so we protect most of our intellectual property with trade secrets. So maybe I should just back up and talk about the difference between patents and trade secrets for a moment. Patents are very important for a lot of biotechnology companies especially. They're a government-granted limited monopoly that lasts for about 20 years after you apply for the patent. But to get the patent, you have to make a lot of disclosures, explain your whole invention, and then when your patent expires, that knowledge is dedicated to the public. Whereas a trade secret is something that is intellectual property because nobody knows it and you never disclose it. So they never expire, but they don't add to public knowledge. But the amount of work that is required to get a patent is very, very expensive. So as a matter of sheer volume, because of the massive number of inventions made at Ginkgo every day, we are focused mainly on trade secrets. But we also have between 50 and 60 patent families and many other starter patents, essentially, that have not yet matured into families, but will at some point. Just to step back and explain what that means, a patent family is essentially like a seed. You make one disclosure of what your invention is, and then you can use that to obtain patents all over the world, in China, in Europe, in Japan, in India, in the United States. So each one of those patent families essentially represents a group of related patents. And so from the patent families that we have so far, we have over 200 issued patents and also a very large number of patents that are pending and are still undergoing examination in national patent offices all over the world. We have a bunch of them that are very much at a starter stage, what are called provisionals, and those will mature to be patent families at some point as well. When Ginkgo makes a new invention, a lot of times what that means is that design engineers or protein engineers will come up with designs for literally thousands of possible proteins or enzymes, biological parts and pieces, that can perform a particular task. And they'll use all their knowledge about biology, our Codebase, to come up with that large set of candidates, which then through our foundry, we're able to screen and figure out which ones actually work. And so when you have the opportunity to try that many things, when you have that many shots on goal, you score a lot of goals. So what that means is that in any particular campaign where we're trying to find one of those important things that is going to make a product for one of our customers, we might have something like 50 to 100 hits that come out of our process. And so then the question is, well, most patents relate to one hit. How do you cover 50 to 100 hits in a single patent? So what we're starting to do is actually make patenting a part of the services that we perform for our customers. We're going to own those patents, but they're going to get a limited exclusive license to a very broad patent that covers an entire hit set and actually provides them with a much broader scope in their market than they would get if they had done this themselves and had found one sequence that worked. The synthetic biology industry has been plagued by not fully thinking through the consequences of agreements and contractual commitments that it made. So there have been problems where people have committed their platform essentially exclusively to one particular customer in a field. And of course, what that means is that if that customer doesn't do very well, the technology can lie fallow. And it also really limits the ability of the company that is supplying the technology to be able to work with others and to generally advance the science that is going to make biology easier to engineer. So I've worked pretty hard to try to develop a transaction structure that allows every customer that we have to benefit from all the previous work that we've done while still also retaining some of that benefit for our future projects. In general, we give, as I mentioned earlier, a limited exclusive license to our customers over patented IP, but we provide a non-exclusive license to unpatented IP and also to the background, to all that other stuff that we invented before we ever encountered that customer. When a company comes to us and is interested in making a particular kind of project, the expectation will be that we'll get into that kind of contract where you essentially give away the store and you say, okay, I'm not going to work in that area anymore. You're going to get exclusivity to all the stuff that we invent. And so sometimes I think they're a little disappointed when they learn that we don't give that kind of exclusivity. But I think that eventually our customers come to realize that our platform is what it is and gives them the power that it gives them because of the fact that we haven't provided that kind of exclusivity. I worked on a project recently where we had done something in the animal feed industry, and we were able to take some of those learnings and use them for plasmid DNA production, which is really super important right now in the global pandemic that we're facing. And so I think that our customers are increasing in sophistication to understand that we really are trying to hit that sweet spot where we do provide them with a real advantage for having invested with us, but we also are keeping our platform moving and growing and continuing to improve so that we can keep making biology easier to engineer.
I see a deep parallel between the heterodox and transformative approach that many companies, including Palantir, are taking in transforming information technology. I see that same parallel with what Ginkgo is doing with the Foundry, with biology, manufacturing, and so much more, everything physical in the world. Another aspect of Ginkgo that I find incredibly exciting is the compounding opportunity of the code base. It's not just data for data's sake, but data that gives you true decision advantage and builds a moat around the business by building and advancing fundamental understanding of the science.